Okay, so let's say we have a problem like this where we need to figure out the molar mass of a compound first. So we've done this before, but let me remind you that if we're finding the molar mass of this particular herbicide, okay, that comes from black walnuts, it has the formula of C10H6O3. And so I'm going to think about each of the components that are in that. So carbon, I have 10 carbons. I have hydrogen, and I have 6 hydrogens, and I have oxygen, and there are 3 of those. And so I'm going to multiply those then by the mass that I get on the periodic table. So 10 times 12.01. And again, this was the mass on the periodic table for carbon. And I'm going to then add that to the mass of my 6 hydrogens. So 6 times, oops, not plus 6 times the 1.01 that we have for hydrogen, and then add to that the mass of my oxygen, so 3 times 16, and add those all together. No dividing, nothing, okay? And so what I end up getting for this is 174.16, and the unit is grams per mole, okay? Kind of like we used in those last conversion factors. So if I want to now just use that in order to convert, it's going to be very much like we did in the last problems, except that I don't have just atoms. So I'm still going to start with what I know, 1.56 times 10 to the negative 2 grams. And I'm going to use the formula here so I don't have to write out, I don't know if it's any shorter. You can use that or the words. And I'm going to use my mass on the bottom, 174.16 grams of the C10H6O3. And 1 mole is going to be what I write on the top. When I then divide that out, I end up getting 8.96 times 10 to the negative 5 moles of the C10H6O3, or if that is not in scientific notation, you should calculate it as 0.0000896. And again, that's moles. So let's try another one, but this time let's try it on your own first. You're going to look at calcite, calcium carbonate, which is really the primary mineral in limestone, marble, chalk, pearls, seashells, things like that. So take a second, pause the video, and try this one. Okay, so you should have calculated the molar mass of calcium carbonate, so we're given the formula there, and you should have added that up to get 100.09 grams per mole. Then we need to calculate first the mass in grams of the sample if we have 4.86 moles. So again, we'll start 4.86 moles of calcium carbonate. And we will convert that using our molar mass, the 100.09 grams of CaCO3 on the top, and 1 mole of CaCO3 on the bottom. And that should give us, we calculated, to be 486.4. But we really need to round that off. We can only have 3 digits since that's what we started with, so we're going to just keep those first 3 digits there, get rid of our 4, and so it'll be 486 grams of CaCO3. Now the second part of this is asking us to figure out the mass of the CO3 ions that are present. So I'm going to actually go back to my 4.86 moles of CaCO3, and I want to think about how many ions are present in a mole of that. So for every 1 mole of CaCO3, I can see from the formula that there would be 1 ion in that formula. So I'm going to say that there would be 1 mole of the CO3 minus 2 ions. Then what I'm going to do is I'm going to figure out, well, what's the mass of just 1 mole of the CO3 minus 2 ion? So I can go ahead and add that up. Again, if I think about my carbon, It's 12.01. My oxygen would be 3 times 16. And so that would end up having a mass of 60.01 grams per mole. So for every 1 mole, it would be 60.01 grams of CO3 minus 2. And so when I multiply that out, I get 291.6. Again, I can only keep 3 digits because that's what I've started with at the beginning. Again, as long as you're within 1, I'm fine with it. And so this is going to round to just 292 grams of CO3, oops, I'm squishing it, minus 2. Okay, let's take a look at one last example. So in this case, we're going to talk about isopentyl acetate, which is the compound that is responsible for the scent of bananas. Interesting fun fact, they will do a lab every year at UW-Madison where the chemistry students make this compound, and the entire chemistry building smells like bananas. Fake bananas, it's kind of like that banana candy smell, but yeah, it's interesting. So bees actually release a little bit of this compound when they sting, and so we want to figure out really how many molecules of isopentyl acetate are released in a typical bee sting. So again, we're going to always start with our, what we know, our 1 times 10 to the negative 6 grams of the C7 H14O2, and I want to turn this into the number of molecules first. So I'm going to use my molar mass, so 130.21 grams of C7H14O2. And again, that's opposite of 1 mole, C7H14O2. Sorry, it's a little messy. And to get to molecules, I know that for every 1 mole of this compound, so C7H14O2, it is going to have 6.02 times 10 to the 23rd molecules. Remember, you can't abbreviate molecules as mole because mole means something different. So molecules of C7H14O2, I know it's really squished in there. Okay, anyway, the answer that we get would be 4.62 times 10 to the 15th, that's a 0, molecules, C7H14O2. But the problem is that when we look back at our starting number, I really only have 1 digit here. So I should really only answer with 1 digit in the coefficient space. And so I'm going to get rid of my 4.62 and round that off to 5 times 10 to the 15th. That's the number I'm then going to use for my second step. So it says how many atoms of carbon are present. And so I'm going to use my 5 times 10 to the 15th molecules of C7H14O2. And I want to get to atoms. So I know that for every 1 molecule of the C7H14O2, just by looking at those subscripts that are in it, there would be 7 atoms of carbon. And so I can multiply that out and I get 3.5 times 10 to the 16th carbon atoms. Again, I mean, if you left it at this, you're within 1, and that's fine, but I really should round this so that there's only 1 digit in the coefficient spot here. So we would round that to 4 times 10 to the 16th. And again, I would have to make sure I have that times 10 to the 16th. So last little bit, just as a reminder, there are some elements that exist as molecules. So we've talked about those diatomic 7. So remember, we start with element number 1, H2, and then we jump over to element number 7 on the periodic table, so N2, and we're going to make a 7. So H2, N2, O2, F2, and then we're going to go down. So Cl2, Br2, I2. So those are our diatomic 7. There are a couple of others to be aware of, but they are not really as common for us to deal with as these others. Phosphorus actually forms a tetratomic form, so it would actually be existing as P4. Sulfur, in its elemental form, has 8 sulfurs that are kind of linked together. And then carbon can have either the diamond or graphite form. We call these network covalent solids, and we'll talk about those later on in the year. But these diatomic 7 are the ones to really be aware of.